Okay, so what I want to talk to you today about pressure-independent rate theory. I'm going to talk basically about transition state theory, start with the derivation of it, then some simple applications, and then some more complex applications in the sequence of the 3 lectures. The derivation I want to give to you is what I call a dynamical derivation. Most textbooks you find what I call an equilibrium derivation. I find the dynamical derivation to be much more intellectually stimulating. You can use it to understand lots of things that people do with advanced forms of transition state theory, like variational treatments and so on. It's much harder to understand what the variational idea is in equilibrium derivation. The dynamical derivation really goes back to Wigner's day, but for some reason the earlier derivations based on Wigner, not Wigner, on Eyring and Polanyi are commonly given in textbooks. All right. So as I said, I'm going to start with the formalism. That will be most of this lecture, and then we'll spend a lecture basically illustrating ab initio transition state theory. How do we couple transition state theory with those electronic structure calculations that we talked about last lecture? And then go and look at more complicated forms of transition state theory, Bayerless reactions, multiple transition states, and then conclude with some discussion about the role for dynamics. There are times, transition state theory makes some approximations about dynamics. It assumes that every trajectory that passes through your transition state surface continues on to products. It comes directly from reactants. That's an assumption, and sometimes, and it doesn't really tell you anything about where your energy ends up. And that's sometimes very important. That's one of the main rules for dynamics. Sometimes it's hard to get a good transition state dividing surface. So there's some rule for dynamics, and we'll try and give some indication of that. So this lecture, the first lecture for today, we're going to talk about a derivation of transition state theory, motivate it, try and go through the derivation, and then just standard definitions of statistical mechanical quantities at different levels. So the canonical level, microcanonical level, and then E and J resolved level. And then go on to the sort of standard forms of transition state theory, conventional, and then improvements beyond that, and then short discussions of accuracy. So motivation, again, what we said last time, we need rate constants for thousands of reactions. Where do we get them from? Experiment, you can't perform experiments on thousands of reactions. Even more problematic, it's very hard to perform experimental kinetics measurements at the temperatures and pressures of relevance to combustion. If you can get your temperature up to 2,000 Kelvin in some kind of shock tube, it's still hard to get that shock tube operating at 100 atmospheres. Theory, we can put in whatever parameters we want. I'm going to only talk about the high pressure limit, which is, there is no pressure independence today, but tomorrow we'll talk about the pressure dependence. Another key problem is you really can't isolate species of interest. A classic example of that is if you look at combustion mechanisms. It's very common for the reaction of HO2 with your fuel to be a key sensitive reaction in looking at things like ignition delay. And it's important at temperatures like 1,000 Kelvin or even slightly higher. HO2 will dissociate on the time scale of most experimental apparatus at 1,000 Kelvin. And so you can't measure its rate constants because it's dissociating at the same time as you're trying to react in, and it just gets all convoluted together. You can make some kind of very indirect measurements, but even those are difficult. Theory has no problem looking at things, no matter how slow they are. So that's one classic example. I'm going to argue, I would argue with you, and I'll show you a little bit of this, that for many reactions, you can actually get a better understanding, a better prediction of the rate constant from good theory than you can from doing an experimental measurement. It's hard to get experimental measurements that are more accurate than a factor of 2 for many reactions. You can actually do better than a factor of 2 uncertainty in your prediction for many reactions from theory. We're sort of in the midst of that transformation of which way is the best way to get at a rate constant right now. But it's not at all a stretch to make that statement for a number of reactions of smaller species. All right. So now within theory, what's the best way to get a rate constant? The most accurate thing, remember we talked about nuclear dynamics very briefly at the beginning of the last lecture, and we said, well, nuclear dynamics is sort of in this transition region between where classical mechanics is appropriate and where quantum mechanics is appropriate. The best treatment is to do a fully quantum dynamical simulation of your nuclei on this electronic potential surface. People do that. They can do quantum scattering theory calculations of reaction rate constants. The classic thing was look at H plus H2. That was the topic of the day in about 1970, 1975. Some of you may know who George Schatz is. He's the editor of JPhys Chem A. His thesis work was doing 3D scattering of H plus H2 and showing that you could get a very accurate rate constant. Why does he do H plus H2? Because it's the simplest possible reaction. It goes over a barrier, and you've got only 3 very light atoms, and so the number of states you have to deal with is very small, and it's a particularly simple. Today, you can do maybe 4 or 5 atom systems. So in 40 years, we've progressed from H plus H2 to things like methane plus H or something like that. You can go a little bit beyond that, but really state-of-the-art calculations are sort of 4 or 5 heavy atoms, 4 or 5 atom systems typically. Obviously, we're not going to map out the reactions of importance to combustion at that level in any kind of rate that's useful to us. The other, the way things are generally done now is you have some kind of empirical model. You got some experiments for some related reaction. You try and extend those by looking at how things vary with heats of formation or other parameters. And that's useful, but sometimes there's no experiments at all. Sometimes you want greater accuracy. Another classic approach, and this is sort of the approach that everybody that does protein folding sorts of things, biochemical simulations, historically has done. They're starting to move beyond it. But historically, the idea is, well, let's just propagate our nuclei according to Newton's equation of motion, and then let's just calculate how fast the reaction happens that way. Purely classical treatments of rate processes are not accurate to orders of magnitude. You've got to do things to get beyond the purely classical approximation. Transition state theory gives you a very simple way to put in quantum effects, especially if you're going to make things like rigid rotor harmonic oscillator assumptions. It becomes a trivial exercise if you're going to make the rigid rotor harmonic oscillator. And so then it becomes a question just of being able to determine the parameters of your transition state. One of the beauties of transition state theory is that it's a local theory. It tells you where is the thing that determines the reaction rate. What part of your configuration space determines the reaction rate. By telling you where that key space is, you can focus your efforts at getting high accuracy electronic energies on exactly that region of the potential energy surface. If you run classical trajectories, you need to have a potential energy surface that maps the whole configurations, all the possible interactions. That then decreases the level of accuracy that you can use in doing that mapping. So one of the key things in transition state theory is this locality that lets you do high-level things in mapping the potential surface. Transition state theory is an old theory. Eyring and Polanyi, I said, developed it independently in 1935. Wigner gave this nice dynamical description in 1936. By the time I started doing transition state theory, it was old and basically nobody was doing it. I'm considered to be sort of worthless in the chemical dynamics community because I'm doing transition state theory, and it's just, well, we already derived that in the 30s. What my contribution is to think about how to actually implement it in a way that's useful to things like combustion. How to implement it in a way that we can get accurate rate constants for large classes of reaction, for lots of reactions. Because the theory is old and sort of denigrated, the whole world, when I was starting as a graduate student, was really, no, the whole world, the chemical dynamics community was very interested in molecular beams and very high resolution. The more state-specific, the better, and very dynamical descriptions. Because I'm doing this thing that's old, there's very few people that are writing review articles. So the list of review articles that I've got here has me in all of them because I'm one of the few people that is doing derivations and advances in transition state theory. The only other person that's really been a leader in the last 20 years in this area is Don Trular. Just the way it is. you can read, if you want to get a good understanding of things, Don Trular has written, I didn't list them all, there's hundreds of reviews that he's written. He's a National Academy member and has done some very nice derivations. Earlier, before this time period, there was lots of work on transition state theory. So let's try and think about what transition state theory is. But before we try and think about what transition state theory is, let's think about what it means to calculate a rate constant with classical mechanics. It's nice to start in a classical world and try and understand what rate constants are and how you can derive them, and then we can try and introduce quantum corrections to that and see how we go from classical to quantum within the transition state theory framework. So this picture up here is meant to represent contour diagram which means the potential energy surface as a function of two coordinates that we just labeled Q1 and Q2. And so you see here, this is the bottom of a potential well. This is an equilibrium, some kind of product complex. We're imagining some kind of reactance starting out here. And if we followed the minimum energy path, it would just come along like this and come in and go directly down here to this minimum. You see there's some kind of tightening of the potential energy surface here. This would probably be where you would put your transition state if you're trying to do transition state theory. You would probably find a saddle point on this potential right here. And so you come along this path, it goes up to a maximum and then goes down to a minimum here. The first thing in thinking about reactions is sort of to think about these minimum energy paths. Trajectories don't actually follow a minimum energy path, but they sort of move around about that minimum energy path. And this is just two coordinates just to try and visualize things. And of course, in reality, all reactions have much more than two coordinates, but just try and get us started thinking. So now how do we calculate a rate constant with classical mechanics? What we do is we take some kind of a dividing surface that separates reactants from products. And then we propagate trajectories. We start a bunch of trajectories on this dividing surface. We propagate them forward, and we propagate them backwards. And we calculate whether or not, first of all, whether or not they are going directly from reactants to products. If we are, then we make this parameter chi here 1. If they are not, then we make it 0. And then we just count the velocity of these trajectories as they go through this dividing surface. The average velocity through there correlates with the average flux of particles from reactants to products. Flux of particles from reactants to products correlates with rate constants. Right? So all we do in trajectory simulations, start a bunch of trajectories according to some kind of distribution, the distribution that you expect them to be on when they start on this thing, and then evaluate whether or not they're going on to reactants or products and evaluate their velocity. Velocity you write as a momentum over a mass traditionally in chemical dynamics. So this is just a velocity, whether or not they react. This delta function means we're going to start things on this dividing surface, and this P of Q and P is just our probability that we had there. Statistical assumptions, you usually make this probability of Q and P is just a random distribution according to the density of those points. So it's what you might call a microcanonical distribution. We'll get to that in a minute. Let me first look at the canonical case. The canonical case, the probability of a given Q and P is just the Boltzmann factor normalized by the total integrated Boltzmann factor. Remember, H is just another form of energy, form for the energy. H is the kinetic energy plus the potential. So we're just writing the energy. So the probability of getting any particular coordinate and momentum, set of coordinates and momentum, is just the Boltzmann factor and the energy of that coordinate divided by some kind of normalization factor. This normalization factor is the classical analog of the partition function. So it's just the probability of that state is just 1 over the number of states that you have, is the way to think about it. So this is the classical expression. You just simply integrate trajectories in time, solve Newton's equations, and then evaluate whether or not they were reactive trajectories and what their velocity is. We can think about this at the canonical level. I started with a better way to think about things generally is the microcanonical level. The microcanonical level, you replace this Boltzmann factor with the delta function. All right? So you just force the energy operator, the Hamiltonian, to be the energy that you're interested in. And then again, you normalize it. This time you normalize it by the microcanonical partition function, which is the number of states. Or I guess in this case, it's really the density of states. the microcanonical J-resolved probability, you just add in, you force it to have the particular angular momentum that you're interested in. When you actually want to calculate a rate constant for an isolated reaction such as this, what you do is, what the real situation is, you have some collision, then it decides whether or not to go over the transition state or not. But it's doing all that at a fixed energy and a fixed total angular momentum. E and J are conserved quantities. They're conserved dynamical observables, right? And so the best thing to do when you calculate a rate constant is to work in this microcanonical J-resolved level, because those quantities are actually. If you think about the canonical level, you don't have a constant temperature for these for a trajectory that's going over there. You have the energy and angular momentum fixed. And so this, as we get to it later, will be found to be an overestimate to the rate constant. This is a slightly less than an overestimate, and this is the best estimate way to do things, to use this. The differences between these three things is on the order of 10% each, typically. They can be quite a bit larger, but typically it's only about 10%. So conceptually, it's a lot easier to think in terms of the canonical distribution, and that's what we'll think about mostly. We'll talk a little bit about the other ones as well. But as you try and think about what things mean, it's always easiest to think in the canonical distribution. And that's why we always start with that. But when I do all my calculations, they're almost always in the microcanonical J-resolved, or sometimes in the microcanonical. All right, so now we want to make some assumptions. And these distributions are already one assumption. These are statistical distributions. These are assuming that you have energy distributed throughout all the space that's available. We call it phase space. Phase space means sets of coordinates and sets of momenta. Configuration space, you think of sets of coordinates. Now, oftentimes, you can integrate out momenta analytically, and so you deal with only the configuration space. All right, so let's think about what the transition state assumption is. And the transition state assumption is you go here to this chi. To think about evaluating this chi requires us to propagate the trajectory far enough so that we know whether we've gone on to reactants or products. That means we can't be a local theory. We have to go until we know where we're getting. We have to propagate things for a large distance. To get a local theory, all we do is we say, oh, I'm just going to call this, I'm going to just let this be 1 every time I cross this surface with a positive velocity. Then I don't have to propagate anything. I just calculate whether I've got a positive velocity or not. If I got a positive velocity, my chi is 1. If it's a negative velocity, well, it can't be a directly reactive to product trajectory, so I just set it to be 0. So we replace this proper evaluation of the reactivity function with a step function. The way I just described it, you should realize that's an upper bound. Every real chi will be either 1. Any time that chi deviates from this, it'll be 0 instead of being 1. And so our step function estimate will be an overestimate to the rate constant. One of the beauties of transitions, one of the things that you should understand about trajectory simulations, it doesn't matter what distribution we use to start things on. We can start it. We could put this dividing surface between reactants and products anywhere we want and propagate trajectories, because we're going to evaluate this chi function properly by going forwards and backwards from that dividing surface anyway. So within classical mechanics, within trajectory simulations, you can start your trajectories on any dividing surface. The only rule for it is that it has to separate reactants from products. So you don't want a dividing surface over here. That would be nonsense. Yes?
So for trajectory B, for example, do you count it once as 1 and once as 0 as it goes in and then goes back out?
Yes.
And then how do you know that it's the same trajectory so you don't count the 1?
Okay. So he's asking us about how do we know what to use for chi for this trajectory B that comes in here, crosses this surface, and goes back. For the trajectory simulation, you follow the whole history of it, and so you look at this and you say that's not a reactive trajectory. It's obviously going from reactants to reactants. For transition state theory, when it crosses here, it's going positive. You would include it. When it's going this way, it's going with a negative velocity. You would say it's not counting, so you put a 0 there. So what you've done with transition state theory is if you counted this trajectory once when you should have counted it no times at all. That's why with transition state theory you get an overestimate to the rate constant. You can have other trajectories that might go and come through and turn around the other way. And those would, again, be counted once when they should be counted 0 times. Sure.
So when you want to generate this map,
Yeah.
right, and you said you don't do, this is not based on quantum mechanical derivation of the map, right?
Yeah, yeah.
So, and the map is basically giving you the energies and the x, the 2 coordinates. What are those two, and how do you know that that trajectory of, like, why doesn't B go a little bit to the other side or a little bit, like,
Okay.
what constrains this?
Okay. So he's asking a little bit about what this contour map here means and how do we get it and what does it really mean when we're talking about these trajectories here, right? So when I say classical mechanics, I said we're only doing classical mechanics for the nuclei. We're still going to do the electronic Schrodinger equation with quantum mechanics. You can never get around that. Okay. So what I'm plotting here are solutions to the electronic Schrodinger equation. Okay. So contours are, what a contour diagram is you think about this line is a line in these 2 coordinates, and I'll give you some example what they are in just a second. It's a line in these 2 coordinates where your potential energy is the same number. So this line has a constant number, say 10 kcals. And this might have 0 kcals for all the potential. This might have minus 10. That might have minus 20 kcals, okay? And so on. And so these are lines of constant electronic Schrodinger equation solutions in coordinate space. What do I mean as coordinates? Imagine you had some reaction that was H plus OH goes to H2 plus O. And you imagine this reaction goes on a line. Then your 2 coordinates could be the H to O distance, the H to H distance, and then an H to O distance, all right? And then you can have some kind of plot of those 2 coordinates along those lines. And you'll have some, that's not a very good example because this is a unimolecular. Maybe it's H plus OH goes to H2O. It would be a better example for this particular plot. Next question. Good.
Another question. Here you put the dividing surface here, and I think the rate, how we count will rely on where we put this surface. And can we just put the surface at the transition state part? And I think that part will be narrower.
Yes. Okay. So he's asking, why do I have my dividing surface here, if I understand correctly? Aren't there better choices for the dividing surface? Okay, and so that's really the next thing we're going to talk about. All right. This dividing surface, where you put it, doesn't matter if you're doing trajectory simulations in terms of the final answer you'll get. But in terms of making the calculation easy, it's much better to put, as he's suggesting, to put the dividing surface here through this saddle point. Because if you think about it, if trajectories are coming, they got energy just below the saddle point, they're just going to turn around and they won't go through this dividing, and vice versa. They're coming here with energy just below. But if they come up over this saddle point and they just get onto the other side, then they're going to likely keep going, and vice versa. If they get over that, and they'll just keep going on. And so then you'll have to do less propagation of your trajectories. It turns out your transition state theory approximation, this assumption of what you're going to put in for chi depends on where you put your dividing surface. I was describing how the transition state theory rate how the trajectory rate does not depend on where you put your dividing surface, but the transition state theory rate that you predict depends very strongly on where you put your dividing surface. You can put it anywhere and you will always get an overestimate, but just how much of an overestimate you get will depend on where you put it. That means that there's a variational principle in transition state theory. The best dividing surface is the one that gives you the minimum rate constant. In this picture, the best dividing surface would be something that sort of goes up and down here. The vertical line there. once I think I made this point, I'll make it again. Once we've got this dividing surface and we've made this transition state assumption, we've got a local theory again. We just have to evaluate basically these kinds of phase space integrals, this kind of integral with this probability on this dividing surface. We don't have to evaluate it anywhere else. We just evaluate it on our transition state dividing surface. So it lets us localize our thoughts to particular regions of space. I've already gone through essentially all of what I have on this slide with words on the previous slide. So we have these transition state assumptions. We get an overestimate. That gives us a variational principle. And then we do variational transition state theory. We consider a family of transition state dividing surface. The best dividing surface is the one that provides the minimum estimate for the rate constant. For barrierless reactions, the transition state might move by multiple angstroms as you vary the energy or temperature. The position of the optimum dividing surface depends on the energy. And dealing with that variation can lead to an order of magnitude change in your estimate of the rate constant. For other reactions with the strong barriers, the variational effects tend to be much weaker, but still up to a factor of 2 or so is not all that unusual. When I get to the examples for the barrierless reactions, thinking about those variational treatments will be central to what we do. For now, what I want to do is take us through particular examples, all right? And what do we end up with? So if we take that expression that we had for the rate constant and we just plug in the probabilities in this step function, we can analytically integrate over the momentum. We can we can analytically drive some simple expressions. At the canonical level, you get what is the common or classic transition state theory expression. It's Boltzmann's constant times the temperature over Planck's constant, partition function for the transition state divided by partition function for the reactant, and then a Boltzmann factor in the energy of the transition state. Usually you think of this as the 0-point corrected energy, typically, and then you think about your partition functions as relative to the minimum for each of the different states. The transitions, the dagger here, the transition state partition function means that we evaluate the partition function for one less degree of freedom. We think about our transition state dividing surface. We think about the coordinate that's perpendicular to that dividing surface. It's a hypersurface. There's one less degree of freedom than the full configuration space. And so we evaluate a partition function for one less degree of freedom. And that one that we've removed, we call it the reaction coordinate. You should, I hope, be used to partition functions from whatever stat thermal class you've had. These are just the same partition functions you will have learned about in those classes. So you know the ordinary definition of a quantum partition function is just the sum over all the energy levels. You may not be so familiar with classical partition functions, but classical partition functions just get written as phase space integrals over coordinate and momentum of the Boltzmann factor. And then there's this normalization factor of the Planck's constant to power n. So our derivation gives us this classical expression. And then we say, oh, well, why don't we just replace our classical partition functions with quantum partition functions? There are some slightly more fundamental things, but it's actually really, really hard to properly derive quantum transition state theory and quantum expressions. But this simple ad hoc idea of just simply going from the classical description to the quantum description works wonderfully well. All right? And you've got all sorts of comparison with experiment and theory, scattering theory, for example, that shows that this idea works. If you try to go one step further, you can analytically integrate over momenta generally, and then you just get some kind of mass and temperature dependent prefactor. And what becomes interesting and difficult and important to treat accurately is this configurational integral. We'll go on in a minute and look at simple cases, rigid-rotor harmonic oscillator, and then these expressions become analytic and trivial to implement. We're also often interested in what I would call the microcanonical distribution. Now we're doing things at a given energy. We get energy resolved rate constant, then the thermal rate constant is some kind of Boltzmann average of this energy resolved rate constant. This expression is sometimes called the RRKM expression. My old advisor was the key developer of methods for doing things at the microcanonical level. Actually, he did things at the microcanonical J-resolved level. You get this. This is the number of states of the transition state divided by the density of states for the reactant. Density of states is just the derivative of the number of states. Quantum number of states, you just sum up over all of your energy levels and ask whether the energy is less than the energy you're interested in. This symbol here is a step function symbol. It means that if this thing inside of it is less than 0, then it's 0. If it's more than 0, then it's 1. So all you're doing is you're thinking about diagonalizing your Hamiltonian for the nuclear motions, get all the energy levels, count them up. Which of the energy levels are below the energy you're interested in? That's the number of states. Right? So the words map into the physical procedure. Just counting up states. That's what it is. And so implementing transition state theory and using transition state theory to make accurate rate constants just degenerates into how good can you count states. So people want to make fun of me and say, oh, you just count states. What's difficult is figuring out good physical approximations for doing this, all right? We're going to tell you the trivial physical approximation of the ridge-rotor harmonic oscillator. But to figure out good physical approximations is the key to making. And the simpler they are, as you try and get more accurate, you have to get more and more correct in various things. You have to think beyond harmonic oscillator approximations, and you have to try and think about mixing classical and quantum effects and so on and so forth. And we'll get into that a little bit, but not as much as one could. There is, again, a simple classical analog of this. The simple classical analog is we integrate over phase space again. Instead of just summing up, we integrate, and we take, again, a step function. We, again, normalize by Planck's constant to the end. Again, our actual derivation, if we just simply plug things in from that last result for the rate constant, we would get this expression. And then, again, we just make this ad hoc classical to quantum jump. We go from classical number of states to quantum states. Why not? If you actually implemented classical number of states, you would get off by orders of magnitude, typically. Again, you can integrate over the minimum analytically, and then you get just mass-dependent factors, and you have this configurational integral of powers of E minus V, the potential, the electronic potential. We need not just numbers, but densities and densities. Again, you derive this classically, and then you make quantum relations. Okay, so those are the classic expressions. If you were to do this and look at any textbook, instead of writing things this way, they'll often write it in terms of free energies. The two results are exactly identical, and the derivations mean the same thing. They don't go through this dynamical aspect of what's going on. But all you're doing is relating a Gibbs free energy to a partition function. You can do that in any kind of statistical mechanics textbook, right? You relate equilibrium constants to ratios of partition functions. And here it's just we got a funny partition function for the transition state because there's 1 degree of freedom less. When we think now about finding the best transition state, what we're doing, we're trying to make this whole thing as small as possible. So what we're trying to do is maximize this thing that's got a negative sign in front of the Boltzmann. And so you're trying to find the position of your dividing surface that has a maximum Gibbs free energy. Sometimes it's useful to separate it into two separate terms. You're trying to maximize the enthalpy while minimizing the entropy. And that's useful in thinking about how things work, for example, with barrierless reactions. In barrierless reactions, you have the enthalpy changing strongly. As the two things come together, you have an enthalpy that's decreasing, and so this factor is increasing. But you have an entropy that's decreasing very dramatically, and so it's the competition between the two that leads to the particular location of the transition state. All right. So now we have an expression. This is our generic expression. How are we going to implement this from first principles? We want to try to completely do away with experiment. Just want to try and calculate rate constants from plugging things into the computer. We talked a lot yesterday about calculating rate constants. Calculating energy levels, all right, with electronic structure theory. So we talked a lot already about evaluating that. Now we need to think about how do we evaluate these partition functions. And this is where a lot of the intellectual thinking goes into. How can you get these most effectively? And so there's all sorts of approximations you can make. And just exactly what approximations you make and how much energy you put into evaluating these energies determine how accurate your ab initio transition state theory is. And so when people ask how accurate it is, well, I don't know. It really depends on what you've done and how much effort you're willing to put into things and so on. If you're really willing to put a lot of energy in, you can count states very well and get 10, 20% sorts of accuracy for lots of cases. But if you're just willing to do rigid rotor harmonic oscillator and some kind of DFT, then you're going to get factors of 10 sorts of errors. And so it just depends how much effort you're willing to put into things. And then how efficient is it? Well, again, it depends on how it's implemented. If you do rigid rotor harmonic oscillator with DFT, you can get a result in 10 minutes. I'm going to show you a result for methane plus H, where we get a result in about 10 minutes for you, where we go actually quite a bit beyond that. But just depends on what you're willing to do. One thing that I won't be able to show you, but what is a question you might ask. So we're making this transition state assumption. I've been talking about the problems in accuracy in terms of how well we actually implement it. But suppose we calculated these parameters with infinite accuracy. We really counted the states perfectly for our presumed dividing surface. And we really evaluated the energy with, to 10 decimal places for the barrier height. How accurate would we be then? We've got a dynamical assumption we're making that we don't cross this thing. The answer to that, again, depends a little bit on how you implement it, because we've got variational transition states and you can sort of vary it, and if you don't vary, then you... But typically, with the best kinds of variational treatments, you still tend to get 10% sorts of overestimates of the rate constant. And I could show you a bunch of comparisons with dynamical simulations that tell you that 10% sorts of errors are sort of implicit in the variational transition state theory methods. Do we care about 10% errors? Not really, because almost never can you get the energy that accurately and or the partition functions that accurately. We are, for barrierless reactions, which are initially a challenging problem, but for now is one of the easier problems for us, we are now able to get accuracy that may be the 10 to 20% level. It's actually hard to tell how accurate they are because experiments don't have that kind of accuracy. We're at the level where we don't really know how accurate just because we don't have a proper test of them. For those things, we actually do apply a 10% dynamical correction routinely just to try and take account of the known shortcomings. All right, let's start with the traditional, simplest way to do transition state theory calculations. They call this conventional transition state theory nowadays. Some people just call it transition state. I like to call it conventional. What is conventional about it? There's really two key assumptions in what I call conventional transition state. Number one, the transition state is just the location of your saddle point. All right? You find the saddle point. You evaluate the Hessian at that saddle point. One direction will have a negative second derivative. So you will get what people call an imaginary frequency. Frequencies are proportional to the square roots of the second derivatives. That coordinate, you just forget about it. Okay? The remaining coordinates are these coordinates that go into your partition function sum for the transition state. Right? So you find the saddle point, do an evaluation of the second derivative of the Hessian, evaluate these frequencies of the transition state, then you have your partition function for the transition state. I'll write down the simple expressions on one of the next few slides, but it's a simple analytic expression. You guys could implement that expression in a few hours, or less probably. All right. So we find that saddle point, we do this vibrational analysis. This rigid rotor harmonic oscillator analysis allows you to get simple analytic expressions for the partition function. Standard assumption for rotations is that we can represent them as symmetric tops. Almost no molecule is a symmetric top, but almost all asymmetric tops are very close to a symmetric top. So the errors that you make by converting a symmetric top to an asymmetric top are really minimal. You can either then evaluate a sum over these energy levels, or you can just convert this to the classical expression. Rotations, remember we talked about nuclei are sort of on the border between classical and quantum mechanics. For combustion temperatures, rotations are always really well treated as classical objects. There's no need to do quantum sums for rotations in combustion. Vibrations, a harmonic approximation, we end up with a potential that's a diagonalized sum of coordinates squared times different force constants. Those map into different frequencies, our standard harmonic oscillator vibrational levels. And so now we can just sum over those values for all the modes that we have in our molecule. If you do all that, you get very simple expressions for the partition functions. All right. We have to think about partition functions for all the different types of modes: translational, rotational, vibrational, and electronic. Translational, you don't care about quantum mechanics. It's a simple expression, just some mass to some 3/2, t to the 3/2. Rotations, again, we almost never care about it, at least at combustion temperature. Vibrations, quantum mechanics is important. Typical vibrational frequencies range from a few hundred to a few thousand, 3,000 for CH/OH stretches. 3,000 wave numbers, even at 2,000 Kelvin, is a pretty big number. And so when you put that in a Boltzmann factor, you don't get a sum over many states. If you don't have a sum over many states, then things are quantum mechanical. If you have many states, then things are classical. There's something called the Bohr correspondence principle. You have many states. The more states you have, the more classical-like your object is. So high frequencies, not very classical. The quantum expression for the partition function is trivial. The classical expression is even more trivial. But you can easily evaluate this. And the electronic partition function you also have to be concerned about is just a sum. And all these expressions are just standard statistical mechanics expressions you can get in any book. Think now about implementing transition state theory. How long do you think it would take you to write a code for conventional transition state theory? If there was anybody in this room that couldn't write a code to do conventional transition state theory in less than a day, I'd be shocked. All right? Because all you've got to do is implement these 4 expressions. And what are the parameters? Oh, some moments of inertia. I see that should be a subscript anyway. And some frequencies. And we're going to get these moments of inertia and frequencies directly from your electronic structure code. So you just have as input these moments of inertia, the rotational constants, the energy that we had in the other one, and you have a conventional transition state theory code. That's why people don't make big deals about having conventional transition state theory codes. They're trivial. If you try and do it at the microcanonical level, it gets a little more complicated, but it should still not take you more than another day. I would be surprised because some mathematicians made a great algorithm for counting states, something called the Beyer-Swinehart algorithm. If you try and just count states naively, the way I would do it, you would get yourself into problems of massive loops for having many modes. If you had a big molecule with many modes, you would try and sum over all these different modes, and you would try and keep if you had 10 modes, you would have 10 nested loops over these things. Turns out that's not very efficient, and you'll run into computer problems. Some mathematicians wrote this algorithm, which ends up being just a double loop and works and is completely accurate. I think that was in the 70s or 80s, I forget what. But if you take this loop, you can then immediately evaluate the vibrational numbers of states. I guess I didn't write it here. So here's the vibrational number of states. And then to get the rotational part, you just convolute that with a rotational density. So you got to do a one-dimensional integral on top of this nested loop, and then you get the number of states. You can then put that into your transition state theory expression. And to get the density, well, then you just numerically differentiate this if you have to. Actually, you can write the expressions properly, but and do them without numerical differentiation. But if you didn't want to think too hard. A book by Gilbert and Smith gives a nice derivation of everything that I've sort of gone through here. It's probably out of print, this book, but I think you could probably still find it on Google or whatever, or Amazon, I guess. And it takes you through from the dynamical derivation all the way on to rate constants at different levels of canonical, microcanonical, et cetera. One thing I've left out so far are reaction path degeneracies. Think about an H atom coming to abstract an H from methyl. All right, so you got 3 H atoms on your methyl, and this H in the transition state corresponds to the H's on a line. You could come in and so you form some transition state here, and then we calculate the partition function. But that partition function isn't going to account for the fact that the H could have come in and abstracted that one, or it could have come in and abstracted that one. So you have a reaction path degeneracy of a factor of 3. There are 3 different ways. So whatever rate you calculate for doing one, you need to multiply by 3. It turns out there's a magic formula for figuring out what your reaction path degeneracy is. That magic formula is that you multiply the partition function by the number in enantiomers and divide it by the rotational symmetry number. And you do that for both the reactants and the transition state. If you have 2 reactants, then you have the product of these 2 magic numbers. I like to call this ratio, 1 over this ratio, the effective symmetry. I like to call sigma over m the effective symmetry number. But anyway, you just take these 2 things, write them that way, and then you have m over sigma for the reactant. You modify your partition function with this factor. So the reactant partition function goes on the denominator. So this goes on the denominator for the reactant, and for the transition state, it goes on the numerator. So let's work this through for this H plus methyl example I was talking about. H is our reactant. It has no enantiomers, no rotational symmetry. So those are both 1 for that. Methyl has rotational symmetry of 6. You can rotate it around by 120 degrees twice, so that gives you 3, but then you can also flip it from one side to the other and get the same thing, all right? And so that gives you another 3. So there's a rotational symmetry number of 6 for methyl. There are no enantiomers in methyl, and so we have a rotational symmetry number of 6 for methyl. Now think about our transition state. We've got the H here sitting some distance away from 1H is our transition state. That's our saddle point. Does anybody want to tell me what they think the symmetry number for this is? We've got these 2 H's here. I can't do my fingers. I can't bend my fingers 120 degrees, but they're symmetrically related. So if I flip this whole thing over, I will get the same state again. I will get the same nuclear configurations. And so there's a rotational symmetry number of 2 for my transition state. So now I've got 6 for this factor for the reactants, 2 for the transition state. I take the ratio of those. I've said it in reverse. It's 1 over 6, 1 over 2. Anyways, it ends up being a 6 over 2 correction factor of 3, which is this reaction path degeneracy. This sounds simple. It turns out this is the thing that is most often done wrong in papers. Once you get enantiomers, people have a hard time thinking. And once you start putting in hindered rotors, which is very common, people start making mistakes. I've even made a mistake in a paper with the symmetry numbers. But when you do it right, you can rationalize the number you get with what you expect from the degeneracy. You can't always just think about the degeneracy. Sometimes that gets you in trouble, but you can always rationalize and make sense out of things. All right. Let's go beyond conventional rigid rotor harmonic oscillator transition state theory. Various key people have made advances in this. I'm not a great historian. These three people take lots of credit for variational transition state theory. I think Bill Haase was one of the first. Trular has done some of the most, and Bill Miller developed something called the reaction path Hamiltonian that seems to, that for some reason gets cited all the time. The basic idea is you go to your saddle point, you find your saddle point, and you remember we've got one direction, one degree of freedom that gives us a negative frequency. That negative frequency corresponds with a certain direction in configuration space. We follow that direction in configuration space forward and backwards, and that defines for us some kind of path. Okay? It defines for, we can do this in some analytic way, and we get what they call the minimum energy path or the intrinsic reaction coordinate. Right. We follow that path, and along that path, we then do more frequency evaluations. We project out the one coordinate that we're following, and we look at frequencies along all the other coordinates. It gets a little bit complicated because now you no longer have zero gradients. If you don't have zero gradients, you don't really have frequencies, but you do some projections, and you can still get frequencies for all your n-1 degrees of freedom. And then you can put in those, and you can evaluate then this transition state partition function for a bunch of different separations. And you can then put them in. We've got a variational principle. Whichever one gives us a minimum is now our best approximation. All right. That's the basic approach that people followed in variational transition state theory. A bunch of projected frequencies along a reaction path. We put that in and we minimize. All right? And again, we can do this minimization canonically, microcanonically, or EJ resolved. The EJ resolved is the best way. It gives us the lowest number. Another important correction is to include tunneling. Don't have any tunneling in classical mechanics, but in quantum mechanics you do. What is tunneling? So we've got some barrier. We've got this, suppose we've got this minimum energy path, and your molecule comes up and hits some point on this minimum energy path and is about to turn around and go back away from proceeding. But then when it hits that, it says, oh, if I tunnel, I can get through to the other side. I can be at the same energy, but I can be now on my product side instead of being on my reactant side. Usually that involves some kind of H-atom motion. Any other motion, the tunneling rate is too small and is irrelevant. But if you think of some kind of H-atom, basically you think of the H-atom as hopping from one place to another, then now suddenly you can be on the product side. And one can calculate those tunneling rates. It degenerates to thinking about the motion on the inverse of this minimum energy path. You got a parabola that's inverted, and now you think about the dynamics on that parameter. That's how you figure out the tunneling rates, and that then the rate of that modifies your rate coefficient. I gave a very simplistic prescription for that. For combustion, tunneling is of only moderate relevance. At 1,000 Kelvin and higher, tunneling is sort of 10% or less in almost all cases. But sometimes when you're doing low temperature combustion, you're interested down to 700, 800 Kelvin. At those kind of temperatures, you start to get factors of 2 or more in contribution, and it starts to be important. Really doing tunneling calculations right is really hard. If you think of what I just described, I just killed the local nature of transition state theory. Now I have to deal with and understand the potential all the way from when it hits this MEP to when it gets to the other side. This tunneling integral, this tunneling rate, it strongly depends on the whole features of the potential surface from where it's going to tunnel. So I mostly don't do real tunneling, decent tunneling calculations because it magnifies the effort by at least an order of magnitude. And it's mostly not important to combustion. But sometimes it is. Trular has done tremendous work at deriving ways to calculate tunneling corrections. And he has a code that he calls polyrate. It's a freeware. You can get it from this site. Recent progress is something called ring polar molecular dynamics. Some of the people in the Green group are doing this now. David Manilopoulos is really the key proponent of it originally. I don't have much experience with that. This is just a nice slide from the Trular group. illustrating variational transition state theory with multidimensional tunneling. So this again is a contour plot. This is for some bimolecular reaction, maybe some abstraction reaction. You start here, you come up, this blue line is our MEP, this dot here is the saddle point. We've got our minimum energy path, and so we're going up a hill, hit a saddle point, and then go back down the hill on the other side. You start by thinking of your transition state as going through the saddle point. You can move it around and you sort of keep it perpendicular to the minimum path, and you get an optimized, what he calls a generalized transition state. This dotted line is the Wigner tunneling path. It turns out Wigner tunneling is almost always useless, but it's the only sort of analytic expression that you can have. He doesn't have it on here because he's not such a fan of it, but Eckart tunneling, basically you take this Wigner tunneling path and you replace it qualitatively with one that goes along the minimum energy path. That turns out to be pretty good for most cases, but not all cases. Just it's bad for just enough cases to really be annoying. But that's mostly what I do. It gives you at least some indication of what you expect the sort of magnitude to be. This red dashed line is what his code will generally tell you is the best tunneling path. You come along and you hit some point here, and then you decide, oh, I can go way over here, and I can tunnel all the way over here, and I can avoid then going up over this saddle point. Low temperatures, that actually starts to be really important. I haven't emphasized, but at room temperature, tunneling is almost always the dominant contribution to reaction. Well, for any kind of hydrogen transfer-related reaction, I shouldn't say always. So he has different approaches. Small curvature tunneling is not so hard to do small curvature tunneling calculations. Large curvature tunneling, optimized multidimensional tunneling are a challenge, even today. I think I'm going to stop there for now, and we'll continue on after our break at 2:20.